Hello everyone. Hi, good evening to all of you. So, we will start with our discussion. So, today we will be discussing previous year's assignment 6 for analog circuits. So, let's start. Okay. So, chalo, let's we have already wasted a lot of time here. So, let's go ahead and try to solve question number 6. A low pass filter is given with an inductor and capacitor into branch 1 and branch 2 respectively as shown in figure 2. Okay. If a low pass filter, this is a low pass filter, is transformed into a band pass filter, what will be the elements of branch 1 and branch 2? So low pass filter will have a response like this, right? That is, at infinity the gain will be equals to 0. Gain will be equals to 0, whereas for a band pass filter the gain will be 0 at the starting, and at the infinity it will be 0. So like this you have to think. And now it is asking what will be the elements of branch 1 and branch 2 to transform a low pass filter into a band pass filter. So try to solve this question and then we'll discuss it.
Option 3 is correct.
Let others also solve.
Name option C.
Okay, what about others? What others think? Okay, so also who was I talking to? I guess I was talking to Banerjee, right? The doubts. So Banerjee, do one thing.
Yes, ma'am.
Put it in the chat box your doubts, and then I will try to solve those doubts,
Okay.
and I will post the video. Okay. So I will be once I am done with it, I will post it. So for others, think intuitively for this question. By intuition itself, you don't really need to put lot of formula or anything. It's a very simple based question. You can solve it by intuitively as well. Okay, so सोचो इस बारे में कि कैसे सॉल्व कर सकते हो. What we basically need is per frequency, that is at 0 we need gain is equals to 0, and at infinite also we gain is equals to 0. Okay. Okay. So tell me one thing. What happens if, let's say, this is inductor, right? What a inductor if the frequency is equals to 0? What happens? How does this inductor behaves?
It behaves as a short circuit.
Okay, yes, very good. And if frequency is equals to infinite, how does this inductor behaves?
Open.
Yes, very good. Similarly, now I want from others what happens to a capacitor when frequency is equals to 0.
Open circuit.
Okay. And what happens to the capacitor at omega is equals to infinite?
Short circuit.
Yes. So for a band pass filter, we don't want any output at 0 and at infinity, right? So if we put in the one inductor in branch 1, we put inductor and capacitor in series. That is, in branch 1, we put inductor and capacitor in series. And in branch 2, we put inductor and capacitor in parallel. That is something like this. So tell me what will happen at omega is equals to 0. What will happen to this circuit?
The input capacitor becomes open.
Yes, so this will be short circuited. It will now here it is open circuited. This is short circuited, right? The inductor is short circuited and the capacitor is open circuited. So if V1 V in is input and VO is output, so we are not getting any output since the network is not connected here. So we are here, even if we are giving V in here, we are not getting output, right? Here V0 is 0 and we are not getting any output, thus no output. Similarly, when VO is equals to infinite, when VO is omega O is equals to infinite, similar thing is happening. Now the capacitor is short circuited but inductor is open circuit, and here also inductor is open circuit and capacitor is short circuit. So here also again this circuit, we are getting this circuit and VO is 0, so we are not getting any output. Thus here in branch 1 we will be putting inductor and capacitor in series, and in branch 2 we will be putting inductor and capacitor in parallel. for a band pass filter. All right. So option C is the correct answer. Okay. Now let's go and solve next question here.
Ma'am,
Huh.
ma'am,
Yes.
ma'am. If we explain in this way,
Huh.
ma'am, if we explain in this way, according to the option three, so option one also correct then, because inductor and capacitor in series then at omega equal to 0, so no input is going to our output.
Yeah. Uh, and no, but see, in series, and another is inductor and capacitor in series. So like this, right?
Yes, ma'am.
Hmm.
But ma'am, input is not going to the output
Huh.
side because of that branch one.
Huh.
So
And branch 2 is also open. And again,
so
when
both.
it's infinite, branch 1 is open. Hmm. Yes, you are right. Yes. Uh, okay.
Could I make a point here?
Haha. Go ahead.
But at a certain frequency,
Hmm.
but at a certain frequency, it must allow that also point.
Here it's a steep.
Uh, uh,
Yes, yes, go ahead. So, yeah.
but at a certain frequency, where XL equal to XC, both becomes short circuit and the V naught is not appears in this case.
Hmm.
So that is not band pass.
Filter.
Yes.
Yes. Got it? Any doubt? So, yes, you are right. Hello.
Yes, no.
Yeah, so yes, he is right. So, this is what is happening. We also don't want it to be short circuit, na, anytime. Hello. 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 Anyone? Hello.
Yes, ma'am. Yeah.
Huh.
Here, ma'am.
Okay. So yeah. So here
Yes, ma'am.
we want a
You are
band
audible.
pass filter. We don't want something to. We want it to filter. We don't want it to pass properly. We don't see. Uh,
Yeah, ma'am. Understood, ma'am.
I'm thinking how to explain it to you in different different way. So, hmm.
Ma'am,
Hmm.
ma'am, for the first option, if the inductor and capacitor in series, so the net impedance is J into omega L minus 1 by omega C.
Hmm. Hello.
So for a particular frequency that omega L minus 1 by omega C equal to 0.
Hmm.
So no output is going outside. So that option will not be uh, counted because
Hmm.
frequency will be in between the 0 and infinity. So in between that, we know the band pass, how the characteristics of band pass.
Hmm.
So in between that, we do not want the output will be 0 or some.
Yeah. Yes. Yes. Correct. Correct. But I want.
So option 3 would.
I want different. Matlab, I want a different kind of explanation. So yeah. So basically, everyone understood what is happening here, but I want to explain it in a different way. So I'm thinking about that. How to like explain it in a layman's term. So is there anyone who can explain it in layman's term? I tried to explain this using this one in layman's term. Now I'm also thinking, is there can there be different solution to explain in layman's term? What you guys think? Other way we can solve it. You see, we are here to discuss. Don't worry that you are wrong or your concepts is wrong or something. You discuss. You openly discuss. We will discuss it and we'll think if it is wrong or right. We'll discuss first. So this explanation you understood, right? Uh, who asked the question, yaar?
The me,
Yes. So
Subham.
you understood the question, right? So in option A, there will be a point where it
Yes,
becomes
ma'am.
short circuited, like something like this is happening, right?
Yes, ma'am. I understood.
So we
The
are
impedance is 0.
so we are not getting any output here. So that is why we cannot use branch
Yes.
other all the other three branches we cannot use, because at some point they are becoming something like this, and we don't want anything like this. So but so we I was also thinking about can there be
Okay.
another explanation for this, but I'm not able to think about it. So let's leave it and go to next question, right? Can anyone else think of any other explanation? Everyone, all of you understood the solution, right? समझ में आया ना सबको? क्या हुआ? क्यों हम नहीं यूज कर सकते और कोई सर्किट? हम यही वाला सर्किट यूज कर सकते हैं. समझ में आ गया ना सबको?
Yes.
यस. ठीक है, तो विल डिस्कस कि कैसे हाउ we can have different explanation, but right now I'm not able to think about it, so let's leave it and go to next question. Which element is the most difficult to implement in a chip while designing the filters and is often replaced with a circuit including ideal op amps? Which filter cannot be implemented using this filter, this method? So it is asking which element is most difficult to implement in a chip while designing the filters. ठीक, फिल्टर डिजाइन करते टाइम कौन सा एलिमेंट होता है इम्प्लीमेंट करना इन अ चिप, एंड
It is inductor.
okay, and what about the filter? Which filter?
The low pass filter.
Low pass filter. Okay, Very good. Why? Bolo.
Because ma'am, for the low pass filter, the inductor should be grounded. So and other filters for the high pass or band
Huh.
pass, the inductors is not uh, grounded.
Hmm.
Because ma'am, we have to go to the means op-amp circuit of inductor. So there is a grounded portion.
Hmm.
So
Okay. What about others? What others think? Which filter cannot be implemented using this method?
Ma'am, here,
Hmm.
ma'am, question is not clear. Here, the thing what which I understood is element, which element is most difficult to implement in a chip while designing filters is inductor. It's clear,
Hmm.
and is often replaced with a circuit including ideal op amps means what does it mean, ma'am?
That this using like inductors are replaced with ideal op amps in the circuit to make.
Okay, but why it is included with a circuit including ideal op amp?
Matlab, I'm not getting your question. What?
Does it means the circuit?
Hmm.
Uh, does the inductor circuit which we designed using inductor equivalent circuit
Huh.
designed using amps
Huh. That's why it's
how must have ideal op amps? Does it mean?
yes. That's why it's tough to implement.
Okay.
That is why, because when we replace it, we try to replace it op amps having the best quality. So that is why it
Ideal
is, yes,
characteristics.
almost ideal characteristics, and that is why it is difficult to implement inductors. So yes, you are correct that the element is inductor. One thing is inductors in nature are very bulky, right? They are very heavy. They are bulky, so which makes them
Yes,
tough
yes.
to implement it. But if we are trying to change the circuit, if we are trying to uh, make inductor implement this kind of include this kind of element in the chip, we use ideal op amps. So we don't have ideal op amps, we have op amps having characteristics almost as ideal. So there we have to matlab, we have to put lot of economically it becomes difficult, right? So this is what it is. The most the element difficult to
Yes.
implement is ideal op amp. Now tell me what filter cannot be implemented using this filter, using this method.
It is low pass filter.
Which one?
Low pass filter.
Okay, why?
Why? Because in other configurations such as band pass and high pass filters, we have the inductor which is grounded.
Huh.
One of the terminals is grounded. But in
Correct.
low pass, none of the terminals is grounded.
Yes. Yes, go ahead.
And the equivalent circuit using op amps and the equivalent circuit of inductor using op amps has one terminal grounded. So we can't replace a low, we can't implement low pass filter.
Okay, yes. So correct, yes, this is the correct explanation. So the inductor here is not grounded, right? It is connected. In other type of circuits, inductors are grounded, and which makes the filter easier to implement. But if in a low pass filter, the inductor has is not grounded and is connected to branch, different branch having different potential and not zero, which is tougher to implement, and thus low pass filter is the correct filter which is difficult, which cannot be implemented using the method where ideal op amps are used. Okay, any doubt, anyone? No. Okay, let's go ahead. A buffer amplifier is given, right, with R1 is equals to 6 kilo ohms and R2 is equals to 120 kilo ohms. What will be its gain? So you have to find out the gain, G or K, whatever. I mean, yeah, you know G. You don't go into the variables here. So you have to find out the gain. R1 and R2 is given, and it's a buffer amplifier.
It is 1 plus R2 by R1.
Yes.
So it is 1
Yes.
plus R2 by R1.
Yes. Let others also solve, and then we'll discuss. Let's take 2 minutes.
Ma'am, I have one question. Can I ask or at the end I ask?
Yeah. You can. No. Let's have it at the end so that we finish this these questions and then we can have discussion.
Okay.
What is the correct answer? Others?
It is option A 21.
Okay. What about others?
Option
Option A. Okay. How you got it? Okay. So tell me first thing. What is buffer amplifier?
It gives the same as the input.
What? Your voice is not clear. What is buffer amplifier? Guys,
The output is same as that of the input.
how?
and it doesn't something.
No. Okay, so buffer amplifier is a kind of amplifier where the we want the input, we want the output almost equal to the input, right? So there, in that cases, we use buffer amplifier used to uh, for buffer. Okay, so yeah, so here v0,
Equal or proportional, ma'am?
huh, proportional but almost equal.
Is it equal or proportional?
Yeah,
Okay.
here it is proportional because it's R2 and R1, but if it is short circuit, right, if it is short circuit, then it is almost like 1. So mostly what we do here is, in a buffer amplifier, what we do is we short circuited we short circuit the this thing, and we put V2 here, and this is infinity. No, sorry, not infinity. This is 0. R1 is 0 and R2 is 0, right? R1, sorry, again I put infinity. R1 is 0 and R2 is 0. Have V1. So almost equals to V1. So mostly what we do is, in a buffer amplifier we short circuit. It's a closed loop amplifier. It has a closed loop feedback. So here, yeah, so we short circuited and we got something like this. But here the R1 and R2 are given to us. Acha, does A max is same for, okay. So here, R1 and R2 are given to us, and the formula becomes like this. The formula for gain becomes gain G is equals to 1 upon R2 plus R1. So we'll put R2 here, R1 here, and we'll get the value of G equals to 21. Okay, got it? Any doubt?
Clear, madam.
Hmm. Okay, let's go ahead and try to solve question number 3. Sorry, question number 9. So question 9 says, transfer function of a band pass filter is given with its specifications. A1 is equals to 40. Cutoff frequencies of this band pass filter are 2 radian per second, 32 radian per second, and omega naught is center frequency, Q is quality factor. What will be center frequency gain? So now you have to find out the gain at the center frequency. What is the center frequency? Omega naught. So you have to find out gain at center frequency. Omega 1 and omega 2 are given to you. A1 is given to you. Okay. So try to put it in this value and you will be able to find out. Sorry. So try to put it in the formula given to you in the classes, and you will be able to find out the gain at center frequency. So I'm giving you 4 minutes. Solve it. Don't shout the answer. Okay, you can shout the formulas, don't shout the answers. After 4 minutes we will discuss it. Okay, let everyone solve. Solved everyone?
Yes.
Okay, very good. What about others?
Yes,
So
ma'am.
Banerjee, I guess Banerjee has solved. What about others? I want to know about other people. Were you able to solve?
Yes, madam. Solved.
Siddharth, good. What about others?
Yes.
Lakshman, Shubham, Suja.
Solved, ma'am.
Okay, very good. What about Suja, Priyadarshini? Were you able to solve? Okay. Chalo, let's solve this question then. Huh. So, we have already discussed. We have already discussed Q, right? We have already discussed omega naught. Omega 1 and omega 2 was given to us. From there, first thing that we have to find out was omega naught, right? First thing we were supposed to find out was center frequency. Since we have to find the gain at center frequency, so that was under root omega 1 into omega 2, that is 2 under root 2 into 32 under root 6 for 8, right? Till here, any doubt till here? No. All right. So from there we have to from there we got quality factor again. So quality factor was also, so here center frequency formula for center frequency gain is simple: a1 into q divided by omega naught. But before that, q and omega naught was not given to us, so we had to find out omega naught and q. So first, already omega 1 and omega 2 was given to us, so we were able to find out omega naught. Then we were able to find out q, that is quality factor, using center frequency and the difference in omega 1 and omega 2, that is 0.2667, right? So
Ma'am,
yes, go ahead.
ma'am, ma'am, how the formula is coming? The center.
Yeah, so
Ma'am, how the formula is coming? The center frequency
this
gain.
is given in first.
Ma'am, I gonna explain this.
Okay, go ahead.
Ma'am, can I explain
Yes,
this?
go
Replace S with J omega. Replace S with J omega first, and then replace omega with omega naught, and apply simple mathematics like for a1s, it is a1 into omega naught by here s square terms becomes minus omega naught square, and that and the omega naught square constant will get cancelled, and you have s with j omega naught into omega naught by q. This j omega naught and upper s will get cancelled, and you will remain with a1 q by omega naught.
Okay, ma'am, understood.
Understood?
Yes, ma'am.
Uh, so so anyways, sir has given this formula directly. So it is s. Basically everything will be cancelled out, and here it will be this term, this term, and this term. These will be left, and others will be cancelled out. This will be minus omega naught, right? It will be cancelled out, and ss will be cancelled out, right? The transfer function itself.
Ma'am, for the other cases also, these things, this process will be followed, right?
You, since it's a transfer function given to you, right? So you can follow this method. Yes, it will be followed for all the frequencies in that pass band.
Okay, ma'am.
So same. So here put it j omega naught, and here it will be minus omega naught square plus j omega naught omega naught by q. I'm not writing all of this because I don't have a pencil. I'm using a mouse to write all these things. Anyways, so yeah, this will be cancelled out, and then this will be cancelled out, and it will be a1 q by omega naught, right? So we have already got omega naught, and we have already got q, right? And a1 is given here as 40. So a1 is given here as 40. Omega naught we have got already, and 8 sorry, omega naught we have got already, and q we have already got. We'll put it here, and we get gain is equals to 1.335. Any doubt?
Okay, ma'am.
Any doubt for others? So I want you to interact with me. Try to interact with me. See, I'm also a student only. Even though I'm a PhD student, I am also learning with you. I learn new things with my students as well. So don't worry about being wrong. You tell me, we'll discuss it, and then decide, right? That way you will also be able to learn something, and I will also be able to learn something new, right? Anyways, let's go ahead. Try to solve question number 10. So a limiter circuit is given in figure 5. If the threshold voltage of the diodes D1 and D2 is zero point 0.6 volts, what are the limiting conditions? So here it's a zero point 0.6 volts. What are the limiting conditions? So this is a limiter circuit, and threshold voltages of diode 1, D1 and D2 is given, and it is asked what are the limiting conditions. So I'm giving you 2 minutes. solve this question and then we'll discuss. And don't shout the answer before 2 minutes. Done? None? Done, everyone. Now you can tell me the solution, the option that you got.
Yes, ma'am.
Yes. Okay. What is the correct answer? What did you get?
Ma'am, option B.
Okay. Very good. What about others? What others got?
Can you explain this?
Yes, I'm going to explain it. What about others? What others have got? What others have got? So our VD is 0.6 volts, right? So whenever our voltage whenever our voltage goes above this 0.6 volts, right, output voltage becomes, 1 second. Okay, so whenever our VU is above VD, right, our diode D2 starts conducting, and D1 is not conducting, right? So it stays at VO, and whenever uh, yes, and whenever our VO goes below minus 5 minus 0.5 0.6, our D2 stops conducting and D1 starts conducting, thus making our VO limit to zero point 0.6 minus 0.6 volts. So what happens basically is a limiter circuit limits the voltage VI in such a sense that uh, VI can be anything. Okay, our VI can go like this, right? It can increase linearly, but here first thing that notice is it's a inverting. So normal ideal inverter, if it is connected to inverting node, then it would have been something like this, right? But here it has diodes connected to it, and thus making it a limiter circuit. So in limiter circuit, what is happening here is, so whenever our VI goes above zero point 0.6 volts, right? So then uh, D2 becomes forward bias, and D1 becomes, yeah. So D1, sorry. So whenever, say VI is above VO, VD. 1 second. So for our diode yeah. So for our diodes to conduct, right? D1 and D2. Yeah. So our diodes to conduct, we need a zero point 0.6 voltage, a minimum of 0.6 volts. So above 0.6 volts, a diode will conduct, and below 0.6 volt, it won't conduct at all. Okay. And whatever will be the maximum voltage, that is voltage here, will appear here. Okay. So before 0.6 volts, there won't be any conduction from the diode part, and another. So when so our threshold voltage is 0.6 volts, right? So whenever it goes above 0.6, it will be conducting, and we will be getting VO at 0.6 volts. That is, it will be appearing, the voltage VO will be similar to the diode voltage, which is maximum it will go is 0.6. The other diode will be reverse bias, so it won't be conducting. Similarly, when VI goes above minus 0.6, this one will be in reverse bias, and it will be switched off, and this will be conducting, and it will be, threshold voltage is 0.6, so it will have a maximum of 0.6 volt, and this is a minus of a maximum of minus 0.6 volt. So this will appear here. Understood what is happening here? So see, let's say it's a,
No, ma'am, it's not clear at all.
okay.
Ma'am, it would be better if you take VI greater than 0 as one case and VI less than 0 as one case. That would be better, I guess.
But 0 won't work. Let's take it as minus zero point 0.6 and plus 1.6. Okay.
And other
So this is
the
threshold.
other point is here virtual short can be applied, right?
Huh?
Actually, as per my knowledge is concerned, when we have diodes, we must perform open circuit test first, and then we have to proceed with the feedback type of the feedback and all.
Mm-hmm. So what are you suggesting? Like, how should we go?
I'm not clear, but first we have to consider for VA greater than 0
No,
how
so
the circuit is behaving, and for VA less than 0 how our circuit is behaving. And ma'am, could you please let me know what type of feedback we are having here? It is negative, obviously.
huh? It is converted to our inverting terminal, lah. So it will be inverted. So our response to
Okay.
our
So there is so what kind of feedback we are having? Either positive feedback or negative feedback. As the output is connected only at the negative terminal and the positive is grounded,
hmm,
then we have negative feedback, right? Am I correct?
yes,
Then we can apply virtual short condition.
apply, and then tell me what are you getting?
Okay. And then here the voltage at the negative terminal, let us take it as Vn, and it is always 0.
Okay. So now what are you getting? So what are the limiting conditions? And first, what does limiting condition mean? First, we have to discuss. So, huh? Go ahead. Limiting condition basically means
Okay, ma'am,
second
proceed.
case.
Proceed.
Huh? So limiting condition basically means that the conditions which is limiting our voltage, output voltage. So those conditions. Okay. So as soon as our
Okay.
voltage VO goes above the threshold voltage, this our D2 starts conducting, and here it becomes short circuit. And as soon as this becomes short circuit, right? As soon as this becomes short circuit, it directly travels, right? And our VO becomes zero.
When the diode D2,
Yes, so D2 starts conducting because the threshold voltage is zero
okay,
point 0.6, above zero point 0.6. So D2 starts conducting, and once D2 start conducting, this is short circuit. So V0 is equals to 0. Similarly, when our V0 is goes below minus zero point 0.6, that is, it goes minus. Now what will happen? The reverse by I mean this this diode D1 starts conducting, because now diode D1 is in forward biased. So now this one starts conducting, this is reverse bias, so this is the open circuit, right? But this starts conducting. Now this starts conducting means ki it is again short circuit. So if it is again short circuit, then VO is equals to 0 again. In between, what will happen? In between, when our VO is in
but
between minus zero point 0.6 to plus zero point 0.6, it will be, our RF will be conducting. Both of these diodes won't be conducting at all. One will be reversed bias, another will be below threshold voltage. So another diode won't be conducting at all, and one diode won't be conducting at all, and one diode will be reversed biased. So it is like switched off. So that won't be working. So our RF will be working at that time.
ma'am, okay, but here, could you please Ma'am, could you please point out the axis?
So yeah, so see, it is something like this.
Yes. What is and mention the x and y axis, please.
So this is our,
And which quantity is on x axis and which
see,
on y axis?
so this is our, vi, right? And this is our vo. So this can be taken as time t, let's say. So now what is happening is, so our here, so one thing is, it is attached to,
Not audible.
hello, see,
Hello.
hello. So this is,
Hello.
hello. Yeah, I'm not speaking. Wait.
Ma'am.
Hmm. See, this is zero point 0.6 volts, right? And this is minus zero point 0.6 volts. Okay. 1 second. So one thing which is happening is, it is getting inverted. Okay. And then it is
Okay.
getting limited to zero point 0.6. Here it's zero point 0.6, and here it is 0 0.6, minus
Then
0.6.
conducts, V naught becomes zero, right?
Where at point, yes, where when vi is 0, it is 0. Yes, yes, it becomes 0. So understood from the curve what is happening. One thing is, it is getting inverted. Another thing is,
But
whenever,
where?
hmm, so whenever threshold is achieved, so after threshold, one of the diode starts conducting and another diode is reverse biased. So when one of the diodes start conducting, it will be taken as short circuit, and the voltage drop it has, so the voltage drop it has will be zero point 0.6
Okay.
volt, and that will be the limiting condition. So that appear on the output voltage. And similarly, in the next cycle,
Okay, ma'am. Okay,
another
got it.
diode will be conducting and one diode will be reverse biased. Got it?
Okay, ma'am. Got it. Got it.
What about others?
Yes, ma'am. Thank you.
What about others?
Understood, ma'am.
Okay. And who else is left? Understood? Everyone? चलो ठीक है. So
Yes, ma'am. Understood.
okay, so now that you have understood, all the best for next assignment. 1 second, am I presenting still? Stop presenting. Okay, so all the best for the next assignment. And if you have doubts, you have already posted. I will try to make a video of that doubt, and I will post it. If you have still, you if you have doubt, you can put it in the chat box, and or you can ask to me right now.
Yes, ma'am.
Ha.
In Miller compensation, I have one doubt. Ma'am, are we intentionally placing the capacitor or I didn't understood whether we have placing the capacitor intentionally or not?
We are placing it now in Miller compensation. So it one is normal compensation. So there we put capacitor. So it's a compensation. First you have to understand it's a compensation, right? So we are compensating for the circuit. So we are intentionally putting the external circuit over the existing circuit. Okay?
We are placing an external
Yeah.
circuit.
So it's a compensation. So we are putting it ourselves. It's not there. Okay. So I guess for assignment 6 deadline is already over, right? Guys, okay, I will copy these and so okay, all the best for assignment 7 then, and I will meet you next week. Chalo, bye bye. All the best. Bye.
Thank you, ma'am.